Okay, this is a homework question. Find the derivative of y equal to tan inverse ln x. The derivative of tan inverse is 1 over 1 plus u squared times the derivative of u, which is 1 over x. So you can tell now you can multiply numerators, multiply denominators. That's exactly what it is. If you have no other homework questions, I will just continue with section 6. All right. So section 27.6, and as you know, this is derivatives of the derivative of exponential. So exponential function is when, or they use b here, when the variable is on the exponent. We call the function exponential. Yes, Sterling. Am I right? Is it not 11 o'clock class? Okay. So everything okay, Sterling? So we just started. It's been 5 minutes since we have started this class. All right. So this kind, like for example, y equal to 2x is exponential function. Its graph is always at 0 to 1, you know, it's always like that. When you go increase on the x, the y will increase indefinitely. And then when you go low on the x, when x is very low, if you go to the left, then the y is never below 0, but it is almost approaching the x-axis. You know, it's almost, when x is, say, what I'm saying is the limit of 2 to the power of x as x approaches negative infinity is 0. That's what I'm saying. If you go to the left indefinitely, then the limiting value for y, the y value, would be almost 0. That's why this is going closer to 0, you know. All right, but the limit of the exponential function as x approaches infinity, if x is 1, is 2, if x is 2, it's 4, if x is 3, it's 8, if x is 4, and so on, this goes to positive infinity. And of course, at this point, it's always 0, 1. For any exponential function with this format, b to the x has to pass through 0, 1, because when the exponent is 0, 2 to the 0 is, or b to the 0 is 1, provided that b is not equal to 0. All right. So we are interested in finding the derivative, not the function, you know. Of course, the domain, or the domain as you know it, is the what x can be, the set of real numbers. The range is always is what y can be. Y is always greater than 0. It cannot even be 0. It's always positive. Any exponential value is always above 0. Always. Think of it as positive. That's why we have the graph above the x-axis. Okay, now the derivative. Now back to the derivative. Now we want to establish okay. So what we have y equal to b to the x, the derivative, or to b to the u, to make it general, b to the u, where u is a function. Dy by dx is actually b to the u. It repeats itself, okay, times ln of b and then the derivative of u. Okay, I just want to remind you what we did with the logarithm. We said logarithm of u, the base b, is the derivative is 1 over u, okay, log of e to the base log of e to the base b, right, times du by dx. We say that, right? That is last section 27.5. Now we want to find the derivative of exponential function b to the u. Why are we interested about, when we talk about exponential, we talk about logarithm. When we talk about logarithm, we talk about exponential. Do you even remember the relationship? You know, logarithmic function is not an abstract function. It is exponential function. When you say logarithm of u to the base b equal to something like z, you can always change this into exponential function. It's b to the z equal to u. Then here you have it as a exponential form. So log means a function which calculates the exponent. See, a function which calculates the exponent of something. So if I ask you what is 2 to the power of what will give me 16, 2 to the power of what will give me 16. Simple math, but you're really asking log of 16 base 2. That's it. So mathematicians, what they want to say, the exponent finding function is logarithm. It's not abstract. What value do you put on here to get 16? It's 4. So that 4 is equal to log of 16 to the base 2, which is 4. So both of the exponential and logarithm are interdependent. Logarithmic function is defined based on exponential functions, and that's why I keep going back and forth. At least that's pre-calculus. That's what you should have done on MTH 128, and hopefully you still remember. Yeah. So this is what the derivative of the exponential function. So one thing is, 3 things, okay? 1 is repeat itself. 2, the ln of b, right? 3, find the derivative of the input. Okay. Yeah, that's it. So the second part, there is a second. Okay, well, maybe I just throw a couple examples to make it clear. Examples. So suppose you have a function y equal to 3 to the 2x. What is its derivative? Dy by dx is, what is the rule state? Repeat itself, 3 2x. Right, ln of b, ln of 3. Find the derivative of u, 2. So this is 2 times 3 to the 2x ln of 3. In fact, ln of 3 is a number. It's a number, a constant. It actually, you can use a calculator, ln 3. It is actually 1.099, approximately equal to 1.099. Right? You could have replaced that, multiplied by 2. No, Sterling. It's ln is log of a function to the base e. E is a number, 2.72. Okay, the base e, not base 10. Base 10 is when we have an log, the common logarithm. When it's ln, it must be base e, where e is a constant, approximately equal to 2.72. So this is what happens. So the product of 2 times ln 3 is 2.197. It's approximately equal to 2.197. The power of 3 to the 2x would be another answer. I will accept this. I will accept this, but this is also okay. Both of them are okay, right? So this is number 1. Number 2, say what is y equal to 10 to the power of cos of x. Find the derivative, right? Find the derivative. Find the derivative of this. Who can help me? What is it? What is dy by dx? Okay, let me see. 10 to the power of cos x times ln 10. Times minus sine x. Excellent. Thank you. Thank you, Dima, too. You contributed in there. Yes. So repeat itself. 10 cos of x times ln of the base, ln of 10, times the derivative of the exponent, minus sine x. When you do minus, you got to use it a bracket, because otherwise you're going to change the whole expression into subtraction. So this is, you can take those two up front, minus sine x, ln of 10, and 10 to the power of cos x. You can multiply these two 10s. You can't touch them. They are under the influence of different functions. So ln 10 could be changed into a number, but it's okay. I will take this as it is. Okay. So my question here is, now how about the derivative of y equal to e to the u, right? What is special about b to the u and e to the u? Their bases are different. You see, the base here is any base b. It should be a base. It can't be anything. It should be a base. It has to qualify to be a base, any base, and in here any base b. But in here it is specifically for e, just like we said before, log of x to the base b versus log of x to the base e. Okay, log of x to the base e is what we call ln x. Log of x to the base b is just the way it is. If it is the base 2, there is not, it's a binary log. If it's the base 10, it's common log. If it's the base e, it's actually natural log. Okay, now we have exponential functions. The exponential function of b to the u versus e to the u. The derivative of b to the u we have seen already. Repeat itself times ln of b times du by dx, we said. So what would be the derivative of u e to the u by dx then? Because what is the difference between this and this? It has a base e. So whenever there is b, replace it by e. Yes, ln e is 1 with some e, right? So b to the u, no, e to the u, repeat itself, times ln of e du by dx. But ln e, as we suggested, is 1. Exactly. Ln e is simply log of e to base e. And we know that when the domain and the base are the same, the logarithmic function equal to 1. So this actually, the derivative of e to the u is simple. It's much easier than any derivative that we consider. This is the easiest derivative. We're saying the derivative of e to the u is itself. Nothing much. I'll give you examples out of my mind, and then we do textbook examples. So what is the derivative of, find the derivative of y equal to, say, 5 e to the 10x squared. So it's e. So it would be easy. So dy by dx would be simply 5 repeat itself. That's the rule. Times ln of e, it's gone because in the derivative of e to the u, there is no ln factor. There is none. In the previous case, we have ln factor because the base is not e. So we always have to keep that. But for when e is the base, there is no ln. You just do the derivative of the exponent, which is 20x. So this is 20 times 5 is 100x. E to the power of 10x squared is the answer for it. The derivative is that 20 times x times 5 is 100x. It's the 10x squared. I just copied it. Number 2. What if it is 2 is the tan inverse of x squared? Make it complicated. Dy by dx. Who can help me? Don't forget. Be strong enough to say. Just repeat the way it is. That's the start of e to the. If you have e to the something, the derivative will be repeat the whole thing. First step. So I repeat, I copy it. And then times the derivative of the exponent. The derivative of e to the u is e to the u times the derivative of the exponent. Really, very easy. So the derivative of the exponent, we have a rule of the tangent inverse. It is 1 over 1 plus the input squared, which is x to the 4. X squared is x to the 4. Times the derivative of the input, which is 2x, really. So this is, I have 2x, I have 2 up top, I have 4x, it's the tan inverse of x squared. On the denominator, I got only 1 plus x to the 4. That was the answer. The 2x times the 2 is 4x. Okay. All right, this much is enough from here. And then I will take from examples from textbook. This is on section 27.6, page 854. So I'm going to take some examples. You can stop me if you're not following. Number 4, what is the derivative? So the instruction is find the derivative. Number 4, it is y equal to 10 to the power of x to the 6. So of course this base is not e, so it's it has that ln factor. So copy. That's the procedure of the derivative times ln of the base times the derivative of the exponent. That's it. So this is 6x to the 5, 10 to the power of x to the 6 ln 10 is a good answer. You can leave it like that. We don't have to change ln 10, but we can find ln 10 to be a number on a calculator. You can do that. Ln 10 is approximately 2.303, and then times 6 is 13.816. You know, that is that. So 10 to the power of x to the 6 could also be a number. Or x cubed in there. Oh, I will take this one as an answer. Both of them are okay. So number 6, we have r equal to 0.3. It's a theta squared. It's a theta squared. So dr by d theta is, of course, this is e. Exponent is e. So there is no ln at all. That will not appear. So this is e. It's 0.3 e theta squared. That's the procedure. You know, d by dx of each the u is repeat itself du by dx. Right? So I copied it times the derivative of u, which is 2 theta. So 2 times 0.3 is 0.6 theta. It's a theta squared would be the answer. All right. Number 8. I have y equal to 0.6 ln of, it's a 3x, it's a 5x plus 3. Again, this is not a, I mean, it's a question of the last section and this section. It's not only this section, because ln was covered last section, but they brought us a question combining both logarithm and the exponential functions. So dy by dx is, of course, what is the derivative of ln of u? It is 1 over u du by dx, isn't it? Just remind you, the derivative of this has no effect. It's as a multiplier, and this derivative is 1 over the input. The input is e to the 5x plus 3 times the derivative of the input, which is itself e to the 5x times the derivative of the exponent, which is 5, plus the derivative of 3 is 0. You know, you don't have to write all this, but you can treat it that way. So what's happening? 5 times, well, 0.6 over it's a 5x plus 3 times 5, it's a 5x. That's what we got. And then I can multiply 5 by 0.6, which is 3. It's a 5x over it's a 5x plus 3 would be the answer. So far, okay? I am okay so far, okay. Number 12 is a product rule. So it is y equal to for each the x sine of half x. So dy by dx, the derivative of this, there are two functions, u, v. When you find the derivative of the product of two functions, it's u prime v, u v prime. You know, you do a linear combination of the primes. So for each x, its derivative is, you know, it's exponential function. The derivative of each x is each x, because this is a number. The derivative of this is a number, which is 1. For each x is the derivative of the first times the second plus the first times the derivative of the second, which is cosine of 1/2 x times the derivative of the angle, which is 1/2. So it is this here, for each x sine of 1/2 x plus this and this are 2 each x cos of 1/2 x. So in here, I can even factor 2 each x. I know this is a good answer. 2 sine of half x plus 2 each x is out, cos of half of x. Yes, when we get there, we will do. Okay. Yeah, you will. We will get to all kinds of difficulty. So number 14, I got u equal to e to the 0.5v over 2v. du by dv is equal to, this is quotient rule, u of v prime is u prime v minus uv prime v squared. So the derivative of the top function is itself times the derivative of the exponent times the denominator function minus the top times the derivative of the denominator over the denominator square, which is 4v squared. Denominator square, part of the formula. So this is 1v, it's a 0.5v minus 2, it's a 0.5v over 4v squared. And then of course you can factor it's a 0.5v into v minus 2 over 4v squared, which is not different. Both of them are good enough. Number 16 is, I think, a product rule, of course, of another product rule, sine of 2x times e to the x squared minus 1. u v prime, as you know it, u prime v minus plus u v prime. That's a derivative of the product of two functions. Dy by dx is equal to the derivative of the first, which is cos of 2x, times the derivative of the angle, which is 2. That's the derivative of u. And then times v, it's a x squared, is it x squared? It's a x squared minus 1 times the, not the derivative, but just times the function v, and then plus u sine of 2x times the derivative of v, which is itself, times the derivative of the top exponent, which is 2x. So here, yeah, 2 cos of 2x.
Should be the minus 1 goes up with the exponential, x
Yeah,
squared.
thank you. Okay, is that what you meant? Yeah, thank you. Okay, here it is a minus 1 right there. All right. So 2 cos 2x e to the x squared minus 1 plus, here I can bring out 2x sine 2x e to the x squared minus 1. You can also factor, it's 2 is common, e to the x squared minus 1 is common, cos of 2x plus x sine 2x is also another, rather better answer. All right, and we'll do chain rule. Number 20 is chain rule, and I have p equal to 3 e to the 2n plus e squared to the power of 8. So dp by dn is bring the 8 up front, 3 e to the 2n plus e to the 2. You don't change the base when you are adjusting the exponent. To the 7 times the derivative of the inside, which is the derivative of, this is exponential function, its derivative is itself. 3 e to the 2n times the derivative of the exponent, which is 2, plus the derivative of e squared, which is 0, of course. E is a number, e squared is a number, the derivative of it is 0, so constant. Okay, so what we get is actually this is 6 times 8 is 48, e to the 2n, and 3 e to the 2n plus e squared to the 7. So I multiplied 3 by 2, which is 6 times 8, which is 48. E to the 2n, e to the 2n, and then the whole base. Is that okay? And maybe we should do number 24. Y equal to 2e x squared plus x squared to the 24 dy by dx becomes then again it's a chain rule or general power rule. If we are given u to the n, derivative would be n u to the n minus 1 du by dx. That's what I'm going to apply. 24, write the base and subtract 1 times the derivative of the base. The derivative of the base is the sum of two functions, and then the first one is exponential, it's itself, times the derivative of the exponent, plus 2x as another factor. So here I could just 24, 2 it's the x squared plus x squared. In here I have what? 2x is common, and then 2 it's the x squared plus 1 is left, right? I see 2x here, 2x here. I can factor that. So eventually almost the same, almost there. 20x, 2x times 24 is 48x, and then 2 is the x squared plus x squared. Did I miss 23 here? Times 2 is the x squared plus 1. Okay. And implicit function is 26. Y equal to, it's the minus 2 over x times 4 ln y plus 1. So dy by dx, let me see, there is no, well, here is product rule, but overall it is a sum of two terms. Okay, so the derivative is the derivative of the first plus the derivative of the second. The derivative of the second is 0. The derivative of the first is product rule. So let's find uv prime as u prime v plus uv prime. Let's do that. So because y is not explicitly written as function of x, then we couldn't find dy by dx immediately, because we're gonna have dy by dx somehow here, you know, because y appears here, right? So it's not like a clean dy by dx equal to a function of x. So the derivative of this 2, the derivative of the first is 4 eta minus 2 over x times the derivative of 2 minus 2 over x. This derivative is what? It's quotient rule. You can take the derivative of minus 2, 0 times x minus minus 2 over x times the derivative of x. Hold on. So I'm using quotient rule. The derivative of the top times that minus 2 times the derivative of the bottom, which is 1 over the bottom squared. So it is positive 2x squared is the derivative. So we're going to need it because the derivative of u is, you have to complete 2 over x squared. Now that is u prime. That's u prime, you know. We have v. V is what? Ln y. Right? And then you reverse the action. Then copy 4 it's a minus 2 over x times the derivative of ln y. What is the derivative of ln y? 1 over y. Is that all? Yes. So it's 1 over y dy by dx because it's implicit differentiation. So this is copied. Then find the derivative of ln y. It's 1 over y dy by dx. I don't know how y is related with x. So, all right. So here dy by dx, and I have dy by dx here. So I'm gonna take the first dy by dx on the left minus the right one for it's a minus 2 over x over y dy by dx. That's what I got here. Should be equal to 4 it's a minus 2 over x now it's 8. 2 times 4 is 8. It's a minus 2x over x squared ln y. That's all. That's what I have here left. This one is taken to the left, so we're okay. Okay, so dy by dx is common. So I have 1 minus 4 it's a minus 2 over x over y equal to 8 it's a minus 2 over x ln y over x squared. Then I want to make this as one fraction, a over b. You know, 1 minus a over b is simply b minus a over b, isn't it? You just do this minus this divided by this. So what I want is y minus dy by dx, y minus 4 is a minus 2 over x over y should be equal to 8 is a minus 2 over x ln y over x squared. Now you can multiply both sides by the reciprocal of the left hand side. Multiply by the reciprocal of the multiplier on the left. So if I multiply that by reciprocal, I get dy by dx. If you multiply that to the right hand side, 8e minus 2 over x ln y over x squared times y over y minus 4 is a minus 2 over x. You're flipping the fraction before you multiply it because we are multiplying by the reciprocal. you can even switch this into positive exponent, so you can multiply it with this. So I could do a little bit better. 8 ln y over x squared e to the minus 2 over x of y over uh, y minus 4 e to the minus 2 over x. So this is 8y ln y over uh, over so over I have to multiply by this over here. So x squared is a minus 2 over x. No, it's positive, right? 2 over x, right? Times y minus 4x squared. You can even keep x squared. I shouldn't have multiplied all over. So this times this times this. So 8y ln y over x squared is 2x over x y minus 4, maybe the compact form of the derivative of dy by dx. Does it make sense? Is there any step that I messed up, or you have a question that you're not clear about? So I'll assume that it's clear. Yeah, it is. It is assumed. Yes. Usually, you would be. Yes, you would be. You would be given that instruction, but like I said, it is assumed to be positive exponents. Better. But like on the test I gave you, you have to write the positive exponent and whatnot. They might give you instruction. Technically, for me, simplification as an answer, most of us we work hard to write it in a positive exponent format, as an answer. As a process, we don't care really. Sometimes even some textbooks they give with negative exponent, as like in electrical engineering. In most of the cases, they say uh, so R over L 1 minus e to the minus 2t over or 1 minus inductance over e to the 2t. They don't like the engineering formulas are R over C 1 minus L e to the minus 2t. So usually they write it in such a way, but it's in math, the instruction is to have the final answer with positive exponents. It doesn't mean it has significant. When you go further in math, that that concept of writing the exponential function in terms of positive is going to be useless. It's not that important anymore. You can write the answer as you wish, you know. But for now, if I want it in positive exponent, I'll tell you, I'll ask you. Otherwise, you're free to give it with negative or with positive. Any other question? Okay, so I'm done with this section. If you have no questions, so I will assign homework on this section. I did from question number 3. Could you do number 3 up to say 31 odd? They are good exercises. So please do them. This is a section 27.6, and page 854. That's it. So technically, I am done. Content of the course is done. There is 27.7, which was, I said, only if time permits. The idea there is 27.7 is L'Hopital's rule, which I don't intend to do a lot because it's extra anyway. But it helps. It's an operator which helps you do limits. So limit of f of x over g of x as x approaches to a would be most likely infinity, will be after, if you apply L'Hopital's rule, it would be limit of f prime of x over g prime of x as x approaches to infinity. This is the rule, what L'Hopital's rule says. This is only possible. This is only possible if the limits are originally what we call indeterminate. Indeterminate means 0 over 0, infinity over infinity, or a combination of the two, infinity over 0, or negative infinity over something over infinity. They are all indeterminate, a combination of this. Indeterminate means we don't know the value. So say, for example, find the limit of 2x over e to the x as x approaches to infinity. Think of this. So this is actually, if you take this f, this is g. What is the limit of f originally? It is 2 times infinity, right? So it's infinity. What is the limit of g, the denominator? It's an exponential function. If you set infinity for the exponent, it will be infinity. So this is indeterminate. So if it's indeterminate, then you can apply L'Hopital's rule. L'Hopital's rule you can apply. Only L'Hopital's rule does the derivative of f of g as f over g prime. That's not true in normal derivative. It is quotient rule, f prime g minus f g prime over g squared. That's the derivative rule we know. But in L'Hopital's rule, if it's for the limits, it works for the limits. You know what I mean? So the limits of f over g is going to be equal to the limit of f prime of g, or the derivative of 2x is 2. The derivative of e to the x is e to the x as x approaches to infinity. As you can tell that this is constant. We know this is when you plug x to be infinity, it will be huge. 2 over a constant over a huge number is clearly not indeterminate. It is actually 0. Or fixed number 2 over extremely growing number to infinity is of course 0. But before, because they were growing both on top and bottom, was difficult to determine. But here, so that's the only section on L'Hopital's rule. Okay, it helps you to find limits in calculus. Okay, is that okay? I'm not willing to do more than that on that section. Okay, all right. So no. Okay, Trevor. So we are technically done here. Technically done with the content here. Done with the content here. All right. But we'll do review like so. If I had time today, I would have started test 1 up to test for review. I would say for review of the exam, I'll remind you, do tests 1 up to test 1 up to 4, and I'll be able to, before our class on Thursday, I'll be able to return back your marks and the answer sheet for test 4. I'm positive. So by Thursday, when we have the 2-hour class, you have your answers, and you can ask me from every. Dima, you can do a few odd numbers. I'm not assigning that because I didn't do it properly. But for 27.6, I assigned homework right here. 27.6 is right here. Okay, 27.7. It's not. You can do a few odd numbers if you want on the section, but I am not assigning. I'm not assigning there. Even on my syllabus, I say I cover this only when I have enough time. Okay, I think I need to pay attention to the students who haven't been doing well on the 2 hours coming next class, and then help them boost their marks. And then we're gonna do those test-like questions from the tests. Okay. So is Dima's question answered? Thank you. Okay. So tests for review of the exam, do the tests 1 and 4, and then you will have answers and tests in there, and no question will be included. No question will appear on the exam from chapter 20. I don't know if I have told you this. From chapter 20, which is trig identities, I will not ask you a question. No question from that. I think it was test 3. Test 3, I guess. It's completely test 3 or partially test 3. So the exam will cover chapters 23, 24, and 27. I don't know, it's very unstable today in this. The exam time is 9 to 12. You have 3 hours. I'll give you a very small exam, which is 4 pages. It will be 4 pages. And then you have 3 hours. So you have lots of time. Nicholas. Any other question? I see quite a few questions coming up. Is that clear? And section 27.7 is not in the exam. Even though we did a little bit of it. So I guess you're okay. Then I'm done for today's class. And if you have no questions, no problem. Thank you so much, Dima, Sivan, everybody. Have a great day. Wissam, thank you, Catherine. Have a great day, Zachary. And take care, Rafal. Thank you.